We will have two special symposia related to hydrogen embrittlement. So I invite you, if you're interested in that topic, to come and join us. I will talk about some new insights related to synergistic action of hydrogen embrittlement mechanisms, and I will show you some expected results. The new one here in Belgrade. It is my real pleasure to present on this prestigious conference some new results. Here is the overview, a little bit about hydrogen materials interaction. Then I will talk about concept of synergistic action of hydrogen embrittlement mechanisms, and we are very pleased that this year we have 10 years of anniversary of the proposal of our health plus heat model, which is proposed in 2015. So I will present the new results and collaboration with various institutions all around the world into unifying and solving the problem of mechanisms in metallic materials. Then new insights and conclusion and key challenges related to so-called unified health plus ED model for the synergistic action of hydrogen embrittlement mechanism in metallic materials. We have 5 essential steps. It's very important that we still don't have a structure integrity model for the prediction and prevention of hydrogen embrittlement. Still, there is unknown things related to phenomenological research of hydrogen materials interaction. After more than 100 years, we still don't know what's going on in hydrogen material. There are a lot of theories. So we have efforts related to multi-scale modeling and simulation of hydrogen embrittlement phenomena, and also development of so-called hydrogen embrittlement resistant material. But hydrogen embrittlement is just one of the hydrogen damages, and we have a lot of problems, particularly having in mind the future hydrogen transition in our society. So this is a very, very hot topic. Also the transportation of hydrogen in pre-existing oil and gas pipelines, and a lot of work in Europe, in China, in US regarding to solve the material damaging due to hydrogen embrittlement. The problem is hydrogen source and how hydrogen enter into metal. We have external and internal hydrogen, which means from the external source or during manufacturing. And we proposed in 2016 the initial structure integrity model based on multiple active hydrogen embrittlement mechanism and correlation with mechanical behavior of material. We're still working on development of predictive maintenance model. Together this structure integrity model and predictive model will provide a reliable and accurate life damage prediction of various metallic components exposed to hydrogen during the exploitation. Everything started in 1875, paper by Johnson. Hydrogen reduced the ductility of and fracture stress of iron and steel. Then we have a seminal work by Professor Robertson, in which they indicate in 2009 that simultaneous action of mechanisms are responsible for the hydrogen embrittlement in metals. And today we can say that the synergistic interplay of both health, but not only health mechanism, but other plasticity mediated mechanisms and heating mechanism of the cohesion of hydrogen embrittlement are confirmed by numerous experimental evidence and through simulation and modeling. So we have a lot of discussion about heating versus health, and I will present you the new insights related to our so-called health plus heat model proposed at the University of Belgrade in 2015, which is nowadays cited more than 1,000 times. Here is the overview of hydrogen embrittlement mechanism from our review paper. As you can see, we have health and hydrogen enhanced plasticity models like IED, HESIV, defectant concept, various mechanisms which indicate that hydrogen embrittlement produce enhanced plasticity of metallic materials. On the other side, we have only one, the cohesion mechanism, which from my point of view is the final failure criteria due to heat activation, liquefaction. We have a brittle failure of components and microscopic manifestation of hydrogen embrittlement. So we have a dual role of hydrogen. They enhance plasticity and decrease plasticity. So there is a problem with that. And we also have two synergistic models. The first one proposed by Robertson Sofronis, health-mediated heat model, which indicates that health is always a preference for heat deactivation, and our helpless heat model, in which dominance depending on critical hydrogen concentration, metallurgical factors, and stress level. So three parameters, but very difficult to estimate the influence of particular parameter. So here is the sketch. I don't have a time to talk about health and heat model during this presentation. People involved in hydrogen know about this model. So here is a graphical representation from our recent paper in which we try to show to broader audience what's going on with health and heat. So we have health mechanism. The acronym is hydrogen enhanced localized plasticity. On the other side, the heat mechanism is hydrogen enhanced liquefaction, and the synergistic action is formulated through health plus heat model and still in development for, let's say, 10 years nowadays. And I will give you the crucial difference between these two models, between health-mediated heat model and health plus heat model. So the initial activity of plasticity and plasticity-mediated initiation of liquefaction is the concept of Robertson Sofronis model that further developed by Nagao and Martin. And our model talk about predominance of one of the mechanisms. So it's not always the case that health mechanism, the governing mechanism of hydrogen embrittlement, which means that we have a full liquefaction mode, and we propose two new concepts. Local heat microincident concept, and we are working with various teams around the world on confirmation and further investigation of this model. So this is the challenging between two groups of mechanism. One is hydrogen enhanced plasticity mechanism. We have various, including HESIF, HELP, and other. On the other side, we have a transition to heat dominance against liquefaction. So that's the essence of concept of health plus heat model, transition between the dominance of one group of mechanisms and only one mechanism, heat. So it's a complex and comprehensive concept that explains the coexistence of mechanisms. Once again, health and other plasticity enhanced hydrogen embrittlement mechanism. On the other side, heat mechanism. And as I mentioned, hydrogen concentration is probably the most important factor, but also the most problematic factor, because nobody knows what's in hydrogen critical concentration, because we can measure critical hydrogen concentration, as we heard in a presentation by Professor, on various scales. So we have at nano and atomic scale, on lower scale hydrogen concentration, we have microscopic average hydrogen concentration, which we can measure. We cannot still measure the hydrogen concentration in grain boundary or at this location. Nobody knows what hydrogen concentration at local level. So that's the problem with this concept. I can say that health plus heat model is nowadays conferred in almost all metallic materials, as you can see in iron, also in all type of steels, including low carbon steel, high strength steel, martensitic steel, high point steel, and very recently, the health plus heat model and transition the mechanism is confirmed in nickel, also in nickel-based alloy, in aluminum alloys, in high entropy alloys, and more recently, also in additive manufacturing alloys. Here is the first paper from 2015, in which we proposed the health plus heat model. As you can see, here we have a hydrogen concentration on the x-axis and have, let's say, ductility or crack propagation resistance on the y-axis. And upon reaching of so-called critical hydrogen concentration, we have a more or less sharp drop in mechanical property, which means that we have a microscopic embrittlement of material. And if we carefully investigate what's going on with the S3 specimen in blue and S4, S3 still have a good ductility and S4 is embrittled. we can see that we have a very similar fracture appearance, which means that we have a ductile failure with microwave coalescence as a result of HELP mechanism, and on the other side we have a transgranular failure area due to heat, which is a brittle failure. But if you carefully see blue and red one, you can see that there is a difference in participation of ductile versus brittle failure. So in both cases, in the case of good mechanical and very low mechanical property, which means low ductility of material, which means that material is brittle, we have a very similar fracture features, and we have coexistence of both mechanism, and that's the essence of HELP plus heat model. So we have a transition between HELP dominance and to heat dominance. Once again, it's not only a HELP mechanism, but also other plasticity related mechanisms like heat related to vacancy accumulation due to hydrogen at some critical hydrogen concentration. So we have a drop in particular ductility. This is the case of high strength metallic materials. In the case of more ductile material, we have a not so sharp drop in ductility and fracture toughness of material, but this is very dangerous for structural integrity point of view, because at some critical hydrogen concentration we have a full brittleness of material, which means that material will lose the ductility as a result of heat mechanism predominance. So we are talking about what group of mechanisms are dominant in the case of HELP plus heat. And that's the continuation of our research. As you can see, we collaborate with United States 4 universities, including Drexel, University of South Carolina, with Australian partners, RMIT, University of Queensland, with Algerian partners, with Austrian partners, Mont University of Durban, and with Brazilian partners. But I'm particularly proud our collaboration with 5 People's Republic of China, with University of Science and Technology Beijing, with Sun Yat-sen University from Guangzhou, and China University of Mining and Technology. So it's an international work on development and further confirmation and what's going on with HELP plus heat mechanism. So you can see here from 2019 to 2025, we published 14 papers. And now I will talk about unified HELP plus heat model and about 2 new concepts, local heat microincident. As I mentioned, we have a ductile behavior of material, but on micro level, we still have localized brittle faults. And that's the essence of localized heat microincident concept, that practically brittleness and ductility works together, but predominance of one of them defined at microscopic level, whether material behaves in ductile manner or in a brittle manner. But at microscopic level, we have a mixed match of all these mechanisms all the time, but one predominates under special conditions. And that's the essence of HELP plus heat model. So the other one is heated prone traps, which means that we have a particular location in microstructure which are prone to decohesion. Decohesion is losing of relationship between atoms. So we have decline of the cohesive strength between atoms in material, which means that we have a difference. Just briefly, I'm very proud of bilateral agreement between China and Serbia with Professor Luo Hong from University of Science and Technology Beijing. We are working together on study of synergy of hydrogen brittle mechanism high entropy alloys for hydrogen-based energy application. As you can see, we have a published paper and this ongoing project for 2 years. Another collaboration with Chinese partner I'm particularly proud is with Professor Li from Sun Yat-sen University. So we published several research papers, including 2 seminal review papers recently in International Journal of Hydrogen and Engineering Fracture Mechanics. Here is the overview of HELP plus heat model published in 2019. As you can see, depending on critical hydrogen concentration and hydrogen concentration is on x-axis, we have at lower concentration some of plasticity-mediated mechanism activity, including HELP, ID, HESIV, and probable HELP-mediated heat. So the local critical concentration is governed by activity of plasticity mediated, but when we approach critical hydrogen concentration, we have a transition to so-called dominant, which means that the cohesion becomes dominance, which doesn't mean that we don't have a ductility. So we still have some sign of help or some other mechanism, but from microstructure point of view and from engineering point of view, the influence of ductility provoked due to hydrogen becomes minor. So we have a transition to so-called dominance, means that the cohesion is a major mode in our material. So we have the cohesion control fracture mode, and in that case, we have on microscopic level hydrogen independent plasticity, not enhanced plasticity, which we have, and that's the major trick with hydrogen. Hydrogen embrittlement is used to enhance plasticity and independent plasticity. We have a change on the effects of hydrogen on metallic material. Here is the overview in our recent paper in Press and Progress in Material Science, in which we trying to show this is within press our mutual work on hydrogen embrittlement, one very tricky alloy. It's a nickel titanium shaped memory alloy, nitinol. So we provide an overview, including the Kelp plus heat model. As you can see, we have Kelp dominated regime, and as a result, ductile failure and some transgranular failure. When we have an increase in hydrogen concentration, we have a transition between Kelp to heat, and then appearance of more transgranular or intergranular failure. So we propose also so-called EG EGTD and PGTD, which means that due to this occlusion mechanism, we can have a transgranular failure in more ductile material and typical brittle failure due to intergranular failure in something like fastener material, nickel-based alloy, material, high-strength steel. So we have two manifestations of heat mechanism, transgranular failure and intergranular failure. Both of them are brittle. So this is the schematic overview for the first time prepared for the community of hydrogen embrittlement to reveal what's going on with hydrogen embrittlement mechanisms. Here is the local heat microincidence concept. As you can see, we have three circles. We're trying to find when the heat mechanisms become predominant in our material. And it depends on the three factors. This is still work in progress. It depends on the global and local hydrogen concentration of material, and particularly the distribution of material, whether it's localized in some area. Also, we have a particular microstructural feature which are prone to be and some are not prone. One example, you have precipitation strengthening alloy, and one type of precipitates when it saturates hydrogen are prone to heat. Other type of precipitates in the same alloy are not prone to heat. So they can accumulate a much larger hydrogen content and didn't produce the drop of ductility due to decohesion. So that's the concept. Hydrogen occupancy is also very important. And we try to show here at small concentration, we have a local heat microincidence. As you can see, we have MBC, ductile predominance, which means that material still behave in ductile manner, but when the material is ductile, it doesn't mean that we don't have a local spots which are brittle failure in material. But for example, in brand water, we have a localized heat activity, but generally speaking, materials still have a good activity and predominance of Kelp or some other mechanism. With increasing hydrogen content, as you can see, we have a lot of accumulation of that heat microincidence, and concept of local microincidence talk about statistically when we have a large enough of heat microincidence in material, then we have microscopic drop of mechanical property and ductility of material. So we always have ductility and brittleness in material, but the participation of microstructural features of that particular activation of mechanism in microstructural rotation define what's going on in microscopic element, how our material behave in microscopic level. So that's still in work in progress, new insights about this concept. This is the confirmation of this concept published in 2020 with Dr. Wasim from Australia. We show here, as you can see in yellow, we have local microheat incidence. in a form of transgranular failure. We have a predominance of ductile failure due to microvoid coalescence, but we have a health dominance, but we have heat microincidence. And when we have a high enough accumulation, is the blue one, as you can see, we have predominance of transgranular failure and appearance of intergranular vehicle failure, but and we have a high hydrogen concentration, but still the health is predominant. And when we have a hydrogen concentration above the critical hydrogen concentration, 5.19 ppm, we have a full heat dominance, but still we have remaining sign of ductile failure due to minor incidence of health. So we have a change of the participation of health and heat incident in our material. Here is the confirmation of health plus heat model in various materials. As you can see, we have a change of health dominance, competence between health and heat, and then heat dominance. For example, in nickel-based alloy, as you can see, we have a very similar fracture appearance, ductile failure, less ductile failure, more brittle failure, and transition. We also have a confirmation in one low carbon steel, but also in aluminum. So that's what I mentioned, that health plus heat model is confirmed in all materials, metallic materials. This is the heat-prone traps. As you can see, localized spots in microstructure, precipitates, twin boundaries, voids, phase boundaries, secondary phases, grain boundary, pre-existing track. Whether that location, when it's saturated with hydrogen, will provide the brittle failure due to heat mechanism application. So that's the investigation of heat-prone traps. And we recently, with Chinese author, together published a paper in International Journal of Hydrology last year, in which we give an analysis of designing improved hydrogen embrittlement resistance based on the effects of hydrogen on what three types of microstructure feature, whether they are prone or not. We investigated wind boundaries in metallic material. We investigated what's going on with grain boundary and with nanoprecipitates. All of these particular nanoprecipitates is very important for strengthening high strength alloy. And we show the effects of coherence between precipitates and phase, in which the semi-coherent relationship is the most beneficial for the improvements of hydrogen embrittlement resistance of material. And we also analyze the effects of pre-twin, deformation twin, gradient twin, and twin orientation on hydrogen embrittlement. On the other side, MC-type carbides, nanoscale size of precipitates, grain interior distribution, and the coherence precipitates we investigate, and related to grain boundary, grain size refinement, special grain boundary, to improve hydrogen embrittlement resistance, and also strengthening grain boundary elements and grain boundary segregation. So that's the factor which define how to design properly the material. And some example of proper design, as you can see, recent research with Professor Luo Hong, high entropy alloys, new one developed in China at USCD. As you can see, this is a very good high entropy alloy, but we have a problem. So we have L1-2 precipitates, which are also known in steel material, which are unfortunately prone. So as a result, we have a drop of mechanical property with hydrogen due to presence of that precipitate. So what's the idea? To change the design principle to avoid that type of precipitates, which are good for strengthening of this alloy and for corrosion resistance of this alloy, but it's not good for hydrogen. And we carefully investigated that heat-prone tap L1-2 precipitates at grain boundary, which is very dangerous location from point of view of heat activation, is unbeneficial. So we have heat dominance, and heat is larger than help. As you can see, white arrow, we have a location of precipitates. As you can see, we have intergranular failure exact location related to this. This is the new research in nickel-based alloy with colleagues from China. We're working on development of advanced nickel-based alloy, as you can see, by applying these two concepts, because we investigate the fundamentals of hydrogen mechanism, but also how to apply that in design of new material for hydrogen future technology, we develop a new nickel-based alloy with a very high resistance to hydrogen embrittlement, and we show this on our mapping of Hell plus heat model from the sketch which I previously showed. So what's going on with the deformation twins, with the introduction of deformation twin and microbands? We provide the dispersion of hydrogen throughout the microstructure, so we avoid the localized hydrogen accumulation at particularly heat-prone traps. So we have a very uniform distribution of hydrogen, which means that due to results of metallurgical engineering, we provide hydrogen embrittlement resistant new nickel-based alloy, because we all know that nickel-based alloy are very prone to hydrogen, as all high-strength alloys. So, conclusion. Global, local concentration, microstructure, and stress strain define the transition between mechanisms. We propose non-health-mediated decohesion, which is totally opposite to health-mediated model by Robertson and Safais. Also, we introduced two new concepts: local heat microincident concept, still in development, and heat-prone concept as a part of unified health plus heat model. The framework is hydrogen mechanism mapping, investigation of their synergy, future work, defining precondition for transition between them, and predominance in metallic material of these two groups of hydrogen embrittlement mechanism. We believe that the deeper understanding of hydrogen embrittlement mechanism and hydrogen is absolutely necessary, because for improving the safety and reliability of hydrogen-based system in a green energy agenda and transition, which will be essential in the near future. Some key challenges, what should be done? Mobile hydrogen deformation interaction should be investigated. So there is still a lot of unknown things related to interaction between hydrogen, for example, dislocations. So the complex and multiple interaction between hydrogen and embrittlement mechanism must be carefully investigated using the bus technique, all the techniques in the world, atomic rock tomography, to carefully investigate lower scale, pricey equipment. That's the reason why Serbian group collaborate with Australia, with China particularly, because of opportunity and capability of Chinese researchers to do advanced experiments in China, which is very important to further provide progress in this type of research. And we must finally reveal probably the most enigmatic part is the hydrogen provoked hardening and softening. So we can also do hydrogen contributes hardening and softening. And the transition between these two phenomena is strictly related to hydrogen embrittlement and complex hydrogen materials interaction, about which I don't have a time to talk, and finally responsible and governing hydrogen embrittlement mechanism in different materials, including the advanced one, with the corresponding ductile, mixed, and brittle fracture mode and transition fracture mode must be investigated, as I showed you.